is actually 3.0 is the same as, oh, I see. Oh, what?
I guess we gotta complete the equation, huh?
Yeah, this is going to be, this one is, it's not quite the number 2 revisited. I thought for a minute it was. It's going to be one where we're going to have to take advantage of the relation between Kc and Kp. And the question is, consider the equilibrium for the synthesis of ammonia. Consider the equilibrium for the synthesis of ammonia, and I just give you Kc.
Yeah, so we gotta write the...
Yeah, you're going to have to go the other way. You're going to go from the mass action law to the actual equilibrium. So the Kc is equal to This is a very important reaction. It's done on a megaton scale every year. And part A, so given this, A. Write out the corresponding equilibrium.
Is that just the balanced equation?
Yeah. So part A is pretty much is a gimme. Part B is going to get a little trickier, but it's it's not that tough. And so so we take it and we go. What is it? What is the mass action?
3H2 plus N2 goes to 2NH.
Yeah, these are the reactants, so the stoichiometric coefficients are the exponents, so I have 3 hydrogen.
Are we assuming that it's aqueous?
No.
Or,
No, actually hydrogen is not.
but then wouldn't it be the power of hydrogen? Did you say that
You mean
before?
not the power, you're talking about the partial pressure.
Partial pressure, yeah.
But I've written it as Kc, which is concentration. The fact that it's
Same
in the
thing.
gas phase doesn't mean that I can't write it as moles per liter.
Yeah, it's equal.
Yeah, it's just, that's the units I'm choosing to use, and ultimately we're going to end up converting it in part B to the Kp expression, the corresponding Kp expression. We're breaking it into actually 3 parts. That's part C where we're going to do that. So here I am, 3 hydrogens, gas plus.
N2.
It's going to be in equilibrium with
2NH3.
2 moles. And like I say, this one's done on an industrial scale every year. So that's part, let's keep this one as part A, B, and C. We'll do it all together. Because A, B, and C are pretty coupled well. Now.
Is it nitrogen gas?
Yeah.
Yeah.
Yeah. Oh, I'm sorry. Thank you. Okay. Because nitrogen is a gas that most of the temperatures and pressures we're going to deal with. In fact, the reaction may be, in practice, they do this reaction at like 400 atmospheres of pressure. It's huge. That's what costs so much. And the elevated temperatures.
So the pressure makes everything go to the right.
Yeah, and yeah, because we could.
Because 2 moles is bigger than 1 mole.
Yeah, because right now, like at room temperature, this particular reaction favors the products. but because of the temperature dependence of the free energy, the reaction, we haven't gotten into kinetics yet, has a high activation barrier, so they have to have high temperatures to get the reaction to occur, and that's with a catalyst. And so what they have to do is, at the elevated temperatures where the actual reaction occurs, the reaction equilibrium favors the reactants. There's very little product. And so that's why they have to do such high pressures to get enough of a pressure of the product, ammonia, which they can then drain off, siphon that off, and pull the process to the right. So they have that's the whole trick in designing the systems. And Fritz Haber, the wonderful human being that he was, got the Nobel Prize for this, called the Haber process. Even though he also is famous for nerve gas in World War I. He stood by smiling while 10,000 people died in horrible agony. He thought it was a good thing. So I don't really have a high opinion of him, but it was because of this process, which we need so much.
Should have won a prize.
He got the Nobel Prize. No. It's not awarded because you're a nice guy. It's based on your work. So now, part B is what is delta N for the process?
Changing moles, right? Just from 4 to 2.
So what is that? Delta N is going to be
4 moles to 2 moles.
Yeah, 4 to 2.
no, it's final minus initial. So it's
Negative
2 moles minus 4 moles equals minus 2 moles. So that's that's pretty much a gimme, and the only thing you can possibly get wrong with it is probably the sign, because most people can subtract 2 from 4 or 4 from 2. And that is
Well, the change is actually, yeah, I guess it's.
the delta is always, by convention, and this has been our convention since 1A, delta always represents final minus initial. So if you keep that in mind, final minus initial, you won't have a problem with that. Okay. Now, part C, this is going to be a little more interesting. This is going to take a little bit, although it doesn't take that much room for the actual calculation. Scratch paper here might get a little thick. So, part C. At 939 KP, 7.3 times 10 to the minus 4th. Atmospheres. The equation. Okay. Sorry. Right, Casey, in terms of KP. Okay, this is this problem. You'll notice I didn't. Let's look at the question a little bit more deeply. Some of this information is maybe extraneous, and maybe it isn't. I'm not asking you to solve the equation. I just want you to write the expression. Okay? And so what we need to do is, and this is where we might get into a little bit of scratch paper, we could just call up from our infinite memory of equations the expression that Kp equals Kc times RT to the delta n, which is something that's easily enough memorized, but I want to try and maybe derive it just for laughs. Okay, so you'll recall, so this, what I'm about to do is scratch paper. We'll come back and revisit this in a moment. Now, we have to take into account the units of RT. Okay? And so,
Isn't it liter atmosphere mole K?
yeah,
Mhm.
recall that RT has units. And it is equal to, this is going to be, well, let's just write it out, it's going to be liter atmospheres per mole K times K. Right? And so that's equal to liter atmospheres per mole. And that is equal to, let's just rearrange that, liters per mole atmospheres. I can rearrange that, they commute. Now, liters per mole, is that anything?
Molarity.
Yeah, that's reciprocal molarity. That's equal to molarity, inverse molarity, atmospheres. Okay, that was going to be, that's going to provide us with a key for relating something that is in, what were we asked in the question? I want to write Kc in terms of Kp. So I'm given something that is going to have units of atmospheres. Doesn't matter what those units are. And I'm going to want to express it in terms of molarity. Okay, so I'm going to have some sort of a conversion factor. This is going to provide us a conversion factor for going between the two. And so I want to go to, which is going to be moles per liter in some fashion. So if I take Kp, which is in some form of atmospheres, so Kp is going to be in atmospheres, because okay. Am I going the right way? Am I going K? In terms of Kp, I want Kc. Sorry. In terms of Kp. Okay, so Kc is going to be converting something that is in is going to be equal to something times Kp. So question, let's just say x times Kp. Now, because Kp is going to, I want to convert Kp, which is in atmospheres, to molarity, which, so x is going to be Kc equals Kp is going to be equal to I've got Kp in terms of atmospheres, so I'm going to want to have atmospheres cancel. This go in, so I'm going to have molarity.
Molarity squared over atmosphere squared.
Molarity. Okay, now